Okay, so ladies and gentlemen, you are welcome, and we are starting the class now. Okay, so you are welcome. So these are the questions that we are going to start with, and the first question says the spectral lines are caused by A. So these are the options. The option A says elliptical revolution of electrons in its orbits. Option B, electronic transition from one energy level to another. C, electrons in the visible region. D, electronic force of attraction between the valence electron and the nucleus. So that is the first question. So, ladies and gentlemen, the first question is actually starting with the spectral lines. The first question is starting with the spectral lines. And the question says the spectral lines are caused by. So, ladies and gentlemen, we need to understand that first, this question is trying to address the questions under atomic spectra. And we need to understand that. What is atomic spectra? So, when we say atomic spectra, it's actually the types of electromagnetic or electromagnetic radiations in which electrons move from lower energy level to higher energy level, or it occur as a result of emission spectra or absorption spectra. So generally, if you have an atom, let's say you have hydrogen as an atom, and remember that hydrogen has one atomic number. So if we draw the electronic configuration of sodium, the first shell will accommodate one electron. And one thing, ladies and gentlemen, that we need to know is that in an element, after you draw the electronic configuration, there are some shells that remain invisible, that are remain invisible. And of course, in atomic spectra, there is a likelihood that electron can be emitted from one energy level to another, or electrons can be transit from one energy level to another. So that is why in atomic spectra, or yeah, in atomic spectra, we have what you call, we have different types of spectra. We have absorption, or let me say we have emission spectra, we have emission spectra, we have absorption, absorption spectra, and then we have what we call uh, continuous continuous spectra. So, ladies and gentlemen, from the word atomic spectra, it means that the spectra is for the atom. The spectra is for the atom, so it's not applying in molecules, it's not applying in a compound. We are talking about an atom. So, therefore, when element absorb energy or emit energy, there is a likelihood that that element will transit one of its electrons, especially the outermost electron, from one energy level to another. So that is why spectral lines are usually caused when there is electronic transition from one energy level to another. But it depends on the types of the transition. Like for example, in a case where we have one electron in sodium, it can move itself from one energy level to another. And what happens in that case? The electrons are moved from lower energy level to higher energy level. But at that point, the electrons are highly excited. So when electrons is under, or when electrons is in excitation state, the electrons can move from one energy level to another. Please, I'm coming 1 minute. Let me answer a call. Okay. So, ladies and gentlemen, what we are saying actually, because you need to understand this. Sorry actually for the inconvenience. So what I'm saying, ladies and gentlemen, the first question is asking questions under atomic spectra. So the question says the spectral lines are caused by what? What causes spectral lines? So generally, when atoms absorb or emit energy, it tend to transit its electron from one energy level to another. So in a normal sense, atoms, like in this case, this is hydrogen atom. So for the hydrogen atoms, it has only one electron. So it has a minimum energy. So the minimum energy that hydrogen atoms has will make the electrons to stay in one on its outermost shell. But once energy is absorbed or the energy is emitted, then there is a likelihood that the electrons will actually move from one energy level to another. Like for example, in this case, let's say there is an energy absorption. There is absorption spectra. In the case of absorption spectra, in the case of absorption spectra, what happened actually, ladies and gentlemen, it occurs when an atom absorbs a specific wavelength of light. And once that happens, there is a likelihood that these electrons will move from one energy level to another energy level. And as I said, in the case of sodium, it has only one shell, but there are some shells that remain invisible. So when an element absorbs or emits electrons, so there is a likelihood, so it absorbs or emits energy, especially when it absorbs energy, so the electrons will move from lower energy level to higher energy level. But in a situation where the element emits the energy, then it will now fall back to its original shell. So that's why we have two types of emission spectra. In the case of emission spectra is a type of spectra where energy is emitted. Get it, ladies and gentlemen. In the case of emission spectra, it is a situation where an atom emits energy. And once the atoms emit energy, because initially it absorbs energy, that is why the electrons transfer itself from its original shell to another shell. So it moves from lower energy level to higher energy level. That's in the case of absorption, because the atoms absorb a wavelength of a specific light. So that is why the electrons move itself from lower energy level to higher energy level. Ladies and gentlemen, I'm making this explanation for you so that because there are so many questions that I saw from the past question paper, so that at least you'll have a good understanding of what atomic spectra means and how to solve some of the questions that are related to this atomic spectra. So going by that, we have three types of spectra. We have emission spectra and we have absorption spectra. So when an atom absorb a wavelength of its when an atoms absorb a specific wavelength of light, there is a likelihood that electrons of an atom should move from the region of lower energy level to higher energy level. But in a situation where the electrons is emitted, that is in the case of emission spectra, the energy is emitted. So therefore, the electrons will fall back to its original state. And as I said, ladies and gentlemen, whenever we said atomic spectra, it only apply, get this, because I saw so many questions related to that. Atomic spectra, it only apply to atom. It doesn't apply to molecules and it doesn't apply to a compound. So that is what happened. That is why it is called atomic spectra. And this atomic spectra, it actually has two characteristics. We have what we call band spectra. We have what we call band spectra, and then we have what we call lines spectra. So what is a band spectra? A band spectra, it is a spectra that is characterized by distinct lines. It is, in the case of line spectra, It is a type of spectra. It is a type of spectra that characterized by distinct lines. It is a type of spectra that is characterized by distinct lines. And each of these lines is characterized by a specific wavelength. So in the case of line spectra, it is one of the characteristics of atomic spectra that is characterized by a distinct lines, and each of that lines is representing a specific wavelength. And that is why, ladies and gentlemen, in the case of atomic spectra, each and every atom has its own spectral lines, and that is why it is used in characterizing and identification of a particular element. Like, for example, let's say you are in a lab and you have a series of samples of the element and you want to identify each of that element present in a different sample. So what are you going to do it? You can apply this atomic spectra, because from this atomic spectra, you can see that each and every element has its own characteristics lines, or has its own characteristic spectra. So using that, you can identify and analyze each and every element. And of course, we have different line spectra. We have Balmer series, we have Lehman series, we have Pipon series, and we have Patience series. So in the case of Balmer series, the N is equal to 1. And then for the N2, we have first line, we have second line. So for the N2, in the case of Balmer series, or in the case of Lehman series, in the case of Balmer series, in the case of Balmer series, please get this, ladies and gentlemen, it is very important. So in the case of Balmer series, N1 is equal to 1. But for the first line in Balmer series, N2 is equal to 2, and for the second line, N2 is equal to 3. So it continues like this. And in the case of Lehman series, the N1 is equal to 2. But for the first line, N2 is equal to 3. For the second line, N2 is equal to 4. So that is why, ladies and gentlemen, you need to understand what series is that. Is it a Balmer series? Is it a Lehman series? If it is Balmer series, it means N1 is equal to 1. For the Lehman series, N1 is equal to 2. So we have different lines. So for the first line in the case of Balmer series, N2 is equal to 3. So you can have this, and of course, you can use a formula to calculate the wave number, or you can use the formula to calculate wavelength. And that formula is called Rydberg formula. We have 1 over lambda is equal to RH into open bracket 1 over N1 square minus 1 over N2 square. So this one we call it the Rydberg formula, and you can use this formula to either calculate wave number or to calculate wavelength of the atomic spectra. So ladies and gentlemen, you can see that the spectral lines are caused by A, the electron transition from one energy level to another. So therefore, the answer to this question is B. So the spectral lines is usually caused, or it usually happens when electrons is moving from lower energy level to higher energy level, or from one energy level to another energy level. That is what happened in the case of atomic spectra. And then we have another question here which says that given that the speed of light is 3 times 10 raised to the power of 8 meters per second, calculate the wave number of light with a frequency of 1.5 times 10 raised to the power of 6 hertz. So here we are to calculate wave number. And how are you going to calculate this wave number? It's simple. Let me clean the board. So therefore, in this case, we are given first from the questions we are given the speed of light. We have v as the speed of light is equal to 3 times 10 raised to the power of 8 meter per second. Then we have frequency, and the frequency is given as 1.5 times 10 raised to the power of 6 hertz. So how do we now calculate this? So there is a formula that says V is equal to F lambda. That is, the velocity of light is equal to frequency times lambda. So therefore, the velocity here is given as 3 times 10 raised to the power of 8 meter per second. That is equal to frequency. The frequency is given as 1.5 times 10 raised to the power of 6 hertz, then times lambda. So now we are going to make lambda subject of the formula. So we now have 1.5 times 10 raised to the power of 6. Here we also have 1.5 times 10 raised to the power of 6. So therefore, this one will now cancel this. Therefore, at the end, we now have lambda is equal to 3 times 10 raised to the power of 8 divided by 1.5 times 10 raised to the power of 6. So now, ladies and gentlemen, from here, what do we have? Please tell me from this, what do we have? 3 times 10 raised to the power of 8 divided by 1.5. What did we have? What do we have? Please write the answer on the comment box. Write the answer on the comment box. 3 times 10 raised to the power of 8 divided by 1.5 times 10 raised to the power of 6. So we have 3 divided by 1.5. So therefore here we have 200. We have 200 nanometer. So we have 200 because this one it is in hertz. So we have 200 meter. So therefore now from here we have our wavelength as 200. So therefore, how are we going to calculate wave number? To calculate wave number is simple. So wave number is 1 all over lambda. So therefore, we now have 1 all over 200. So 1 divided by 200, what do we have? 1 divided by 200. We have 0.005. Therefore, which is something as 1, 2, 3. So therefore, we have 5.0 times 10 raised to the power of minus 3 per centimeter. So therefore, the answer from here we can see clearly is option B. So B is the answer. So ladies and gentlemen, I hope this is clear. So let's move to another question. So we now answered 2 questions. So we now answered 2 questions. So let's look at another question. Please, I want you to have your calculator so that you can be very active. So let's look at another question. And ladies and gentlemen, I want to say this. Please, if you are hearing me and you are with me, please comment on the box. So here we have another question. The question says, given that, question 3, given that the Rydberg constant, given that the Rydberg constant 109,737.32 per centimeter. Calculate the wave number. Calculate the wave number of the second line of the second line in the bracket series. In the brackets, So ladies and gentlemen, I think you can see this question very well. Given that the Rydberg constant is 109,737.32 per centimeter, calculate the wave number of the second line in the bracket series. So ladies and gentlemen, I now have a question. For the bracket series, N1 is equal to what? For the bracket series, N1 is equal to what? For the bracket series, N1 is equal to what? Please answer me. For the bracket series, N1, okay, is it okay? UTIC says is 5. So do you agree with him for the bracket series, M1 is 5? For the bracket series, N1 is what? So Fatima Sadiq said is 4. Okay, so let's see. So for the bracket series, of course, N1 is equal to 4. I agree with you. Excellent, Fatima. So if N1 is equal to 4, then sorry, here is N1. So if N1 is equal to 4, so what is going to be N2 in this case? So remember, I just finished explaining here. So if N1 is equal to 4 and N2 is going to be 5, 6, 7, 8, 9. So for the first line, in the series, N2 is equal to 5. But here is the second line. So for the second line, N2 is equal to 6. So therefore, we are now going to use N2 is equal to 6 at this point. Ladies and gentlemen, please, do you understand? Okay, Umma Isa, she already answered the question. But let's see. So for the bracket series, N1 is equal to 4. So, but it is very, very important, ladies and gentlemen, if you know this number of series, but understand at what line, because that is where most of you are getting it confused. So since it is at the second line, so for the first line of M2 is equal to 5, and then for the second line, M2 is equal to 6. I hope you now understand. So therefore, from here, you can now use, because the question says we are to calculate wave number. And what is wave number? We just finished calculating wave number. Wave number is 1 all over lambda. So therefore, we now have 1 all over lambda as wave number is equal to Rydberg constant open bracket 1 all over m1 squared minus 1 all over n2 squared. And I think from here it's simple to get the answer, because we have this. So I think without wasting much of my time, or without wasting much of our time, we can easily get this. So we have 1 all over lambda is equal to 109,737.32 open bracket 1 all over 4 square minus 1 all over 6 square. Please, I am advising you, ladies and gentlemen, try to understand how to do most of these things. I'm telling you, if you can check most of the questions, there are a lot of questions from this atomic spectra. So understand them and how to solve them. It's not about just going through the past question paper, it's about understanding. So therefore now we have 1 all over lambda is equal to 109,737.32, then open bracket 1 all over 4 square is 16. That is 4 times 4 is equal to 1 over 16. Then minus 1 all over 6 times 6. So ladies and gentlemen, 6 times 6 is what? 6 times 6 I think is 32. So we have this. 6 times 2 is 32. So do you agree with me? 6 times 6 is so it's 36. So therefore we now have 1 all over lambda is equal to 109,737.32. Then we now have 32 minus 16, 32 minus 16 divided by, so this 32 times 1 we have 32. Then 16 times 1 we have minus 16. So you can now see this time that is 16 times 32. So here is 36. Sorry, it's 36, it's not 32. So therefore from here we now have 36 here. So 36 times 16. We now have 576. Then we put this in bracket. So therefore we now have 1 all over lambda is equal to 10,737.32 open bracket 20 divided by 576. So ladies and gentlemen, now what I want you to do, multiply, please multiply 10,737.32 times 20 and tell me the answer. So we have 20 times 10,737.32 times 20, so divided by 576. So therefore we now have 1 all over lambda is equal to 372.824 per centimeter. So I hope, ladies and gentlemen, it is now clear. So you see, the question says we are to get web number. So web number is 1 all over lambda. So 1 all over lambda is this. So I hope, ladies and gentlemen, you are now clear and you understand how we arrive at this answer. So without wasting much of our time, we can, please, is this question clear? Are you clear to this question? Okay, so let's move to another question. So this is actually question 3. So we solve question 3. So you see, all this question from question 1, 2, and 3, they are all from atomic spectra. So that is why I did a video on atomic spectra. So after we finish with this class, I will advise you to go and watch that video on atomic spectra. I'm very sure you are going to enjoy it. So now, the next thing that we are going to look at is also another question. So the questions that we are going to look at now is the valence electrons of copper are described by which of the following quantum numbers? So in these questions, a set of quantum numbers are given. A set of 4 quantum numbers are given as the option. So the question says, okay, where is the valence electrons for copper? The valence electrons for copper the valence electrons of copper are described by the following quantum numbers. So a set of quantum numbers are given, and you are asked to identify which of the quantum numbers is best described. Yeah, excellent. Is nanometer. Is per nanometer. So therefore, the question says the valence electrons of copper are described by the following quantum numbers. So option A is given as, we have n equals to 3, l equals to 2, and then we have M is equal to plus 2, and we have S equals to plus half. Then option B, we have N equals to 3, N equals to 2, M equals to minus 2, and then we have S equals to minus half. Option C, we have N equals to 4, N equals to 0, M equals to 0, S equals to plus half. And then for D, we have N equals to 4, we have N equals to 0, we have M equals to 0, and then we have S equals to minus half. So the questions here is asking, which of the following quantum number is best described the valence electrons of copper? The valence electrons of copper. And remember, the copper is one of the elements that. Okay. So you know that when we say N is 3, it means that the energy level is 3 and N is 2. So when you have N is 2, remember the last time I told you when you have N equals to 0, it means you have S orbital. When you have N equals to 1, it means you have P orbital. When you have N is equal to 2, it means you have D orbital. So when you have N equals to 3, you have F orbital. So therefore, here for the first option, we have N equals to 3. So it means we have 3, and we have N equals to 3, it means we have 3D. And then we have M equals to plus half, sorry, plus 2. So since it is D orbital, so D orbitals usually have 5 subshell. It has 5 subshell. 1, 2, 3, 4, 5. So the first one is minus 2. Then we have minus 1. We have 0. We have plus 1. And then we have plus 2. So therefore, here it says plus 2. It means that the electrons is here. So since the electrons is here, so it means we have to start arranging the electrons here. 1, 2, 3, 4, 5. But since this one is plus, because remember, according to Hund's rules of maximum multiplicity, Hund's rule of maximum multiplicity said that electrons are arranged into the general orbital singly before pairing start taking place. So because here our M is plus 2, so that is why we have to arrange electrons singly and drop them here. So are we to go back and pair them? No, because the S is positive. So since it is positive, so we are going to stop here. But what makes option A and option B different? Of course, the N is 3, so we have it. The N is 2, so we have 3D, of course. But M is equal to minus 2. So since it is minus 2, so what we are going to do in this case, let me delete this. So it means that we are going to start arranging electrons like this. So we have to arrange it first. 1. So because here is minus half, it's minus half. And remember, the range of value of spin quantum number is plus or minus half. So if it is minus half, it means that you have to start arranging the electrons in all positive half. So therefore, we now have 1. Then we now have another electron 1 here. Then we add another electrons, and then we add another electrons here. Then we add another electrons. So we arrange them singly. But M here is minus 2, and S is minus half. So therefore, you have to pair this. So because here is minus 2, so that is why we are going to stop here. That is why we are going to stop here. So we have to count the electrons. 1, 2, 3, 4, 5, 6. So this is the 6th electron. It means that here is 3d6, and then here we have 4s2. So remember, for the electronic configuration of transition element, you start with argon configuration, then you have 3d6 and then 4s2. So when you have argon plus 2 is 20, then plus 6 is 26. So is 26 a copper? No. Copper is having 29 and 26 is not the atomic number of copper. So this to tell you this one is not the answer and this one is not the answer. So let's move to option C and C. Which one is the correct answer? So when we move to option C, we now have, okay, we now have N. We have N is equal to 30. We have N. Okay, let me delete here. Let me clean here. So which element has atomic number 23? Please write it on the comment box. Which element has atomic number of 26 in the transition among the first transition element? So which of the element has atomic number 26? Please write it on the comment box. Excellent is Fe, that is iron. So now for option C, we have 4, and then for L is s orbital, so we have 4s, and then we have M is 0. Of course, for the M, the electrons are usually the electrons do not actually, it has only one subshell. It has only one subshell. So we have 4s. So after we have 4s and we have our M is 0 and then we have our s is half. So we now have 1 electron here. So it means that in the 4s we have 1 electron. So we have 4s1. So remember that the 4s is the last electron, is the last energy levels of the element with this electron configuration. So therefore we can put other elements. So how? So we have argon configuration, then we have 3d 4s1. So since we have 4s1, it means that of course the 3d is completely filled. So that is why here we have 3d10. So we have 3d10 4s1. So therefore here we have argon plus 1 making argon 18 plus 1 19 plus this we have 29. So this is tells you that the correct answer is option C. So option C is the quantum number that describe copper. It's a quantum number that describe copper. So now let's look at another question, ladies and gentlemen. So which of the following element has the least electron affinity? The following set of elements are given and asked that which of the following element has the least electron affinity. So which of the following element has the least? When we say least, it means lowest electron affinity. So first, we are nitrogen is in the option, that is nitrogen. And then B, we have oxygen. And then C, we have fluorine. And then D, we have neon. So which of the following has the least? Which of the following has the least electron affinity? Please, what is the answer? Which of the following element has the least electron affinity? We have nitrogen, we have oxygen, we have fluorine, and we have neon. So which one has the least electron affinity? Excellent at Ionic. The answer is neon. But what is electron affinity? I think I have to use this medium to explain what electron affinity and some other periodic properties of the element. So when you say electron affinity is the amount of energy that is required to attract electrons to what is the ability of an element, or is the energy, or is the measure of energy that an element requires to attract electron toward itself. That is why sometimes electron, the word affinity, it means it is attracted. The atoms, they easily attract electrons toward themselves. So, but in this case, the electron affinity is like the energy an element has. The energy an element has, or is the amount of energy that a particular element has to attract electron toward itself. So that is why, because it is like an energy that an element used to attract electron toward itself. That is why it is measured in joule. So it has a unit, joule, that is the same unit as energy. And of course, so how do we know that the element has strong electron affinity or low electron affinity? So electronegativity, to know whether the element is metal or non-metal, is very, very important. Like for example now, let's say in the case of nitrogen. So nitrogen, is it a metal or non-metal? Nitrogen has an element, so it has atomic number 7. So the first shell has 1, 2, 1, 2, 3, 4, 5. So it has 5. So there are 3 bonding pair, meaning that this element is a non-metal. Remember, all elements that have electrons 5, 6, and 7 electrons on their outermost shell, they are said to be non-metal. And non-metals, they are elements that can accept electrons for them to become completely filled. So what I want you to understand here, ladies and gentlemen, the nitrogen, if you look at it, it has 2 5, so it has 5 electrons on the outermost shell. So that means nitrogen is a non-metal, and it has a very strong electron affinity because it is a non-metal, so it can easily attract electron toward itself. So that is why nitrogen is one of the elements that have high electron affinity. So the more the electron affinity of an element, the more the electronegativity of that particular element. So that is why electronegativity is directly proportional to electron affinity. So now the next thing is oxygen. The next thing is oxygen. So between oxygen, like oxygen, it has atomic number 8. So we have, first here we have 1, 2, then we have now 1, 2, 3, 4, 5, 6. So it has 2, 6. So it has 6 electrons on its outermost shell. So it means that it is also non-metal. So it has a strong electron affinity. But ladies and gentlemen, I have a question. Between nitrogen and oxygen, which one have the strongest electron affinity, please? Yes, I agree. The answer is neon, but I'm just trying to give some explanation so that at least when we come any questions that's related to that, then we can easily answer it. So now, between oxygen and nitrogen, which one has the highest electron affinity? They are, is it Utic? He said oxygen. Do you agree with him? Do you agree with him? Is it oxygen or nitrogen? Is it oxygen or nitrogen? Truly speaking, the answer is not oxygen. It's not oxygen. Why? Because of the half-field stability of nitrogen. If you take nitrogen, the more stable the atom is, then the high chances it has to accept more electron. And why? Look at it. Nitrogen has 7, so it has 1s2, 2s2, and then we have 2p3. So you see, here we have 1, 2, 3. So we have 1 electron here, 1 electron here, 1 electron here. And then we now have 1, 2. Then we now have 1, 2. So you see, because phi orbitals accommodate a maximum of 6 electrons. But in the case of the nitrogen, it has 3 electrons. So it means 3 is half of 6. So in terms of stability, nitrogen is more stable than oxygen. So that is why electron affinity of oxygen is high, of nitrogen is higher than that of oxygen. Also, when it comes to ionization energy, that is an energy that is required to remove electron from the most loosely bonded electrons. The nitrogen also has more electron affinity than oxygen, and also it has more ionization energy than oxygen at the same time. But for the fluorine, it has 9 and it has 7 electrons on its outermost shell. So that is why fluorine is one of the elements that has the that have one. It's one of the elements that has high electron affinity. So it is the element that have the highest electron affinity. So you may be asked to arrange this element in order of increasing their electron affinity. You may be asked to arrange them based on their increasing electron affinity. So you can see that the electron affinity of neon is less than the electron affinity of oxygen, and then the electron affinity of oxygen is less than the electron affinity of nitrogen, and then the electron affinity of nitrogen is less than the electron affinity of neon. So therefore, in this case, neon, because it is a non-metal, it is an inert element. It doesn't. It is electron. The electrons on the atomic side is completely filled, so it doesn't need even to accept any electrons from any other atoms. So that is why it has least electron affinity. So the answer is D. So please, can I use this medium to explain the other periodic properties of the element, or we should continue? When we come to any other questions, then we look at them and answer them at the same time. So I think that would be the best. So now, the emitted light of an atom consists of the emitted light of an atoms, the emitted light of an atoms. Let me look. The emitted light of an atoms, the emitted light of an atoms, the emitted light of an atom consists of A. The emitted light of an atom consists of A. Consists of option A, the series of lines of the same frequency. The series of lines, the series of lines of the same frequencies. Then option B, the series of lines of the same frequency, the series of lines of the same energy, the series of lines of light, the series of lines of the same energy, and then we have option C, the series of lines of different wavelengths. Different wavelengths then we have option D, series of lines, the series of lines of the same wave number, Ladies and gentlemen, which one is the correct answer? Emitted light of an atom consists of A, the series of lines of the same frequency, the series of lines of the same energy, the series of lines of different wavelengths, the series of lines of the same wave number. Please, what is the answer? Excellent, Mr. Justus. The answer is when an atom emits light or absorbs light, it releases it releases a series of lines, and those series of lines they have different frequency, and the type of the series of lines emitted by each and every element differ from one another, and it's because of that differences in lines of the atom emitted with different frequencies. That is why you can use atomic spectrophotometry to identify the element. Like for example, if you want to identify an element, the series of lines emitted by potassium is different from the series of lines emitted by hydrogen. It's different from the series of lines emitted by calcium. So a lines, a series of lines are usually emitted from the atom, and each of that lines it has a different wavelength. So that is why you can use that in chemistry for identification of different elements. So therefore the answer to this question is option C. So that is why I said, ladies and gentlemen, please, I advise you, most of the things that we answered them here, go and watch my video on atomic spectra. It is very, very, very important. Then the next thing, here we have another question. You see, this question says calculate. The question says calculate, calculate, calculate the wavelength, calculate the wavelength, calculate the wavelength, calculate the wavelength of the third line of the third line of the third line in the Fashion series. Fashion series. Given that Rydberg constant is 107.32 per centimeter. So please, ladies and gentlemen, look at this question. The question says calculate the wavelength of a third line in the Fashion series given that the Rydberg constant is 109,737.32 per centimeter. So now, what is the N1 of Fashion series? What is the N1 of Fashion series? Calculate the wavelength of the third line in the Fashion series. Excellent, excellent, just and you care, excellent. So Fashion series, for the Fashion series, M1 is equal to 3. So what is going to be N2? Because the question says the third line. So if it is third line, then what is going to be our N2, please? Excellent. The N2 is equal to 6. Why is it that N2 is equal to 6, ladies and gentlemen? As we said, for the Fashion series, M1 is equal to 1. So for the M2, we have first line. So for the first line of Fashion series, M1 is equal to 4. For the second line, n2 is equal to 4. So it's equal to 5. And then for the third line, so that's why here I said the third line. So n2 is equal to 6. So that is why we have n2 here as 6. I hope it is clear. So now with this, I think you can easily apply the Rydberg constant. This is the Rydberg constant. But ladies and gentlemen, I realized something from this question. We have 1 all over lambda is equal to Rydberg constant, open bracket 1 all over n1 squared minus 1 all over n2 squared. So you have your Rydberg constant already given as this, and then you have your n1 is equal to 3, and then you have your n2 is equal to 6. So please, I wanted you to do this calculation and get the answer. At the end, you will see that in the option, there is no correct answer. Because at the end, after you do all the calculation, you will see that at the end, you see that the only options that you have is for the web number, but there is no answer for the wavelength. Remember, web number is 1 all over lambda, and then wavelength is the lambda itself. So if you check the option after you do this calculation, you will realize that there is no answer for the wavelength. Rather, the answer given there is only for the wave number. So please, ladies and gentlemen, get this, and I hope you will really enjoy this video, and I hope you are getting the concept. Please, are you following me? The way we are taking the class, are you okay with it? Are you okay with the way we are handling the class? I'm waiting for your comment, please. Okay, Femo said yes, sir. Okay. Okay, so you are following. Okay, so let's look at the next question. The next question. So we have a question here which says that if m, that is a magnetic quantum number, has values of -2, let me. So if mi, that is magnetic quantum number, if the magnetic quantum number has a values, has a values of -2, -1, 0, +1, and +2, the corresponding value of n, the corresponding value of n is, so we have option A2, option B. Option B, we have 1. Now option C, we have 3. We have 3. have 3. Then option D, we have 4. So please, what is the answer? Okay, just to say 3, Abdul Khair said 3. So the answer is what? The answer is 3. Correct. The answer is 3. So you see here, the magnetic quantum number is given as this. So it means that from here you can see that if magnetic quantum number is given using this range of value, so this is to tell you that you are N. It means that at this point your N is equal to 2. And if you have N is equal to 2, what is the corresponding value of N? It's simple. So remember, N is always equals to N minus 1. N is equal to N minus 1. So how did we get N equals to 2? It's simple. It means that when N is equal to 3, when you have your N equals to 3, it means that N is equal to 3 minus 1, that is why you have 2. So it means that when N is 2, then your M is going to be minus 2, minus 1, 0, plus 1, plus 2. So therefore the answer is 3. So you are correct. You are correct. So let's look at another. Let me tell you, I think from this first question paper, I realized 2 things. Number 1, you shouldn't allow yourself to enter into this exam without understanding atomic spectra. And to understand that atomic spectra, please, I advise you to go and watch my video. Go and watch my video, and also this general tutorial that we are doing. I'm telling you, and also I have a video on quantum numbers. Please go back and watch those videos. Look at another question here. It says, which atomic orbital has a values? Which atomic orbitals? The question says, which atomic orbitals? Which atomic orbital has values of n equals to 2 and n equals to 1? So which atomic orbital has this value? So remember, when n is equal to 1, it means that you have p orbital and we have n, so you have 2p. So it means that at this point you have 2p. So this is the atomic orbital. And the options here, we have 1s, we have option B, we have 2s, and then option C, we have 2p, and then option D, we have 3D. So you can see option A, option B, option C, option D. So if n is 1, it means that you have p orbital, and you have your energy level as 2. So that's why you have 2p, ladies and gentlemen. I think this is clear. Are you following? Are you following? Okay. Then another question, look at it, the number of atomic orbitals possible for n equals to 3. The number of atomic orbitals possible for n equals to 3. The number of atomic orbitals for n equals to 3. The number of atomic orbitals possible for n equals to 3 is A is equal to 4, B is equal to 5, C is equal to 9, and then D is equal to 3. So what is the answer to this? Okay, just to say 9. How did you get 9? Tell me, how did you get 9, Justice? Yeah, how did we get 9? I think I have to start asking you this question. If n is equal to 3, what are the possible atomic orbitals? What are the possible atomic orbitals when n is equal to 3? So how did you get the answer? How did you get 9? Why 3 square? How do we, okay, S plus P plus D. And here you said S equals to 1. Other methods are long for CBT, but I didn't see, okay, you said S equals to 1, P is equal to 3, and D is equal to 5. So you now add 1 plus 3 plus 5, and that gives us 9. So you just actually wanted to waste your time by following that method. If you want to calculate the number of the atomic orbitals, you just only square the principal quantum number. You square the principal quantum number, so it's just n square. So n square is the formula that you can use to calculate the atomic orbital. So the total number of atomic orbitals in a shell, the total number of atomic orbitals in a shell can be calculated using n square. The total number of atomic orbitals in a shell is equal to n square, and the n here is 3, so we have 3 square, which is equal to 9. So this is the answer. So I don't know why are you saying that the method is long. So if you want to calculate the total number of atomic orbitals in a shell, so you use n square, and that is why we have 3, and 3 square is equal to 9. So please, is there any question regarding this? So let's also look at another question. I hope we are all following the class. I'm trying to check where the questions are. Okay. This is it. So now, let me put the computer charge. So now, let's look at another question. Okay. I think I have to explain this because I realize that I also see it. I saw so many questions regarding to that. So I think the most important thing is actually getting the explanation. If you are able to get most of the explanation, I'm telling you, you will not have problem with writing the examination. So in case even if they didn't repeat the questions, you can navigate. So the question says the correct order of increasing radii, atomic radii, that is the radii. So these are the atoms. We have sodium ion, we have magnesium ion, we have fluoride ion, and we have oxygen minus. So the question says we are to arrange this in the correct order of increasing atomic radii. So radii. So now that is something that I want you to understand. So if you look at this, you realize that this is magnesium ion, this is sodium ion, this is fluoride ion, and oxygen ion. So now the question is, what is atomic radius? What is atomic radius? Atomic radius is the distance of electron from the nucleus to the outermost shell for an atom that either loses or gains an electron. Like normally we have atomic radius, let's say atomic radius like this. So the atomic radius is the distance between the nucleus and the outermost shell. That is atomic radius. And this atomic radius generally increase down the group, so it increases down the group and it decreases across the period. It decreases across the period. So, but now the question is, what about atomic ionic radius? Ionic radius. So when we said ionic radius is actually a distance of electrons from the nucleus to the outermost shell of the anionic atom. So like for example, this is sodium. So in a situation, ladies and gentlemen, where we have an element, that's where we have the cations, their ionic radius usually decrease. So for the cations have decreased. The cations have decreased ionic radius. They have decreased ionic radius. They have decreased ionic radius. While for anionic, that is anions, those that have negative charge, they have increased ionic radius. They have increased ionic radius. So it means from here, the more the element gain an electron, the higher its ionic radius. So that is why now here, look at it, between oxygen and fluorine, which one gain more of electrons or more electrons? The answer is oxygen. So oxygen gained 2 electrons. So therefore the ionic radius of oxygen is higher than the ionic radius of fluorine. And then between sodium and magnesium, which one loses more electron? Magnesium. So therefore, the ionic radius of magnesium is lower than the ionic radius of sodium, and then the ionic radius of sodium is lower than the ionic radius of fluorine, and then that of fluorine is lower than oxygen. I hope you now understand. Is that clear? So what would be the correct order? So that's what happened. In the case of ionic radius, for the anions, the ionic radius usually, for the anions, the ionic radius increases, and then for the cations, the ionic radius usually decreases. So it means that the ionic radius of sodium is lower than the ionic radius. The ionic radius of sodium ion is lower than the ionic radius of magnesium, and then the ionic radius of magnesium is lower than the ionic radius of fluoride ion and is lower than the ionic radius of oxygen. Or you can decide to say, since we are taking it in an increasing order, so this is, I think this is actually an increasing order. So we can actually take it this way. So now, Let's look at another one. What is the formula of a compound formed between magnesium and oxygen? What is the formula formed between magnesium and oxygen? So first, we need to understand the valency of magnesium. It has two H2, so it means that it gives out two electrons. So therefore, the valency of magnesium is 2. And this is oxygen is 2, 6. It means that it can accept 2 electrons. So therefore, the valency of oxygen is 2. So you can cross. This one can cross with this, and this one can cross with this. So you can have magnesium 2, oxygen 2. So this one will cancel this. You will now have magnesium oxide, GO. So ladies and gentlemen, I think I have taken some of my time. So maybe we are going to stop here. We'll continue with the discussion in the WhatsApp group, and also yes, we'll discuss more because time is going and I want to go. So we'll discuss more on the WhatsApp group. So ladies and gentlemen, thank you and see you next. And I hope you enjoy the class. Okay, you think we will discuss it because it is getting late, so I'm going home. So we'll discuss that on the WhatsApp group. So see you next time and bye bye.